So when this landslide came down off Mount St. Helens, it kind of went in three different directions. Part of it slammed into Spirit Lake, which we can just barely see the tip of Spirit Lake right over to our side over here. And when it hit the lake, it would almost be like a sumo wrestler jumping into a bathtub. It hit the lake, displaced all the water in the lake. A big wave sloshed all the way down to the far end of the lake. The water sloshed 800 feet up the hillsides on the opposite end of the lake. The water sloshed back down in seconds. When it came back down, it landed on a new lake bed covered with this big landslide deposit, and that pushed the water up and over a larger surface area, doubling the size of Spirit Lake in just a matter of seconds. And that's why we can see Spirit Lake from here at Johnston Ridge today. We wouldn't have been able to see it from here prior to the eruption because the lake was much smaller and it would have been tucked a little further back in between the ridge lines over there. Now that's pretty impressive, but most of the slide didn't go into Spirit Lake. Most of it hit Johnston Ridge, which is the ridge we're standing on here in either direction. And down the far end of the ridge towards Spirit Lake, you can note on the top of the hill over here in two locations, there's lots of little lumpy mounds of earth. The lumpy mounds of earth are the landslide deposit, and they're called hummocks. A hummock is a fancy word for a small hill, but what you need to remember about a hummock is it's a big block of Mount St. Helens. Each one of those is a chunk of the volcano that was falling off the mountain during this landslide. As the landslide actually had enough energy to flow all the way across the valley floor and ramp up and over Johnston Ridge in two locations over there, a ridge 5.5 miles away from the mountain and 1,200 feet above the valley floor. But the bulk of the landslide smashed head on into Johnston Ridge, and when it hit the ridge, it scraped away all the soil, exposing bedrock. But the big thing it did is it bounced off the ridge, and this directed the landslide down the North Fork of the Toutle River Valley. That's the big valley everyone parallels as they drive up to Johnston Ridge along State Route 504. The landslide traveled 14 miles down the North Fork of the Toutle River Valley in 10 minutes, raised the valley bottom by an average depth of 150 feet. But in one location, just below us here, on the other side of this ridge, you'd actually have to go down 640 feet to get to the 1980 soil. So if you remember the bulge, I talked about this molten rock. There was all this molten rock that pushed up into Mount St. Helens when the volcano became active. And a lot of people come to Mount St. Helens and say, where's the lava? Well, there was no lava when Mount St. Helens erupted because this volcano erupted a kind of a different type of molten rock. The lava in Hawaii is very red and fluid. It's called basalt. And because it's fluid, gases inside that molten rock can escape very easily. So that's a type of molten rock that flows out of a volcano. It tends not to blow out of a volcano. And if it does, it just kind of splatters. It doesn't travel great distances. The molten rock inside Mount St. Helens is called dacite, and it's thick like toothpaste. So it makes it very difficult for gases inside that molten rock to escape. So this is a molten rock that pressurizes. Just like if I had a bottle of soda and I shook that bottle up, and then if I was to turn that bottle at you and open the cap, you wouldn't be very happy with me, right? Because it would spray out. Well, the landslide, as it came down, released all this molten rock from pressure, and gases inside that molten rock rapidly escaped, and they blasted apart the molten rock, and that's why rocks were flying out the side of the mountain. And if we look at the hillside right behind us here, you can see lots of light gray rocks as well as a lot of other colored rocks out there. The light gray rocks are pieces of that bulge that were flying out the side of the mountain at speeds of 450 miles an hour. And the other darker rocks are rocks that used to be on the north side of the mountain but were propelled out here by this in this stone-filled wind. So when I use the word stone-filled wind, you can just look at the hillsides around us and you know exactly what I mean, because you can see the effects of the blast had on the trees here. You know, we either have just shattered stumps, or if we do have a tree trunk, most of these tree trunks are very small, and you can, well, I should say these are big trees, but you don't see very much of the tree left because the branches were just stripped off and the tops of the tree were snapped off and carried away. I think I mentioned earlier, the blast started off as a stone-filled wind, but by the time it got to Johnston Ridge, it had become a stone and wood-filled wind because these rocks were shattering the forest and carrying little pieces of it away. And it's the trees that were knocked over or shattered here helped blow down trees farther away from the volcano. When the big ash plume went up on May 18th, sections of that plume collapsed under the weight of the cloud. Kind of like if you've cooked spaghetti noodles too long. There's the foamy, frothy stuff. It rises up out of the pot, but it's too heavy to go up, so it flows over the edge of the pot and down the edges of the pot and makes a mess. Well, the big ash plume that went up in the air, sometimes it was too heavy to rise, and it would collapse and flow down the flanks of the mountain. These are called pyroclastic flows. They're hot gas, ash, and pumice rocks that were flowing down the flanks of the mountain. And there were at least 18 of these pyroclastic flows that came tumbling out the north face of the mountain, and that's what created that broad, flat plain directly behind us. The big thing about a pyroclastic flow is that they're extremely hot, about 1,300 degrees Fahrenheit. And pumice rocks with all the little holes in it makes a great insulator, so that the pyroclastic flows remained hot for a long time after the mountain blew. You could have seen steam vents down there in the pumice plain as late as 1985 because those deposits remained so hot.